Okay, so we're on chapter 8, and that's for PTSS, Predetermined Time Standard Systems. So PTSS is nothing but it's just a technique of motion study and time standards development. So what we're trying to do in this method is we're breaking the work by human or machine into basic motions, and each motion has been reduced to a specific time value. So here work is divided into motion 1, 2, 3, and motion 1 is divided into motion element 1, and then you're measuring that motion element time value. And you're already doing it in the lab, okay, first round. So PTSS is nothing but your workstation design, your motion pattern development, and time standards. And is best used before production begins or starts. So we're talking about the current state, and that's your accumulated PTSS, what you have in hand. So we usually use the current PTSS to evaluate the improved methods idea and compare and study. And this is what PTSS provides us, thus to develop the best method, establish the time standard, help develop the standard, establish labor cost, help justify better tooling, help select the best machine for the job, and so on and so on. Okay? So MTM is from 1948, and this group, Maynard, Stagmerton, and Shrub, they developed this MTM family, and that is the best known predetermined time system. MODAPS are nothing but your modular arrangement of predetermined time standards. So it's a PTSS, and it's most consistent for manual work tasks. And the system is easy to use with times based on observed movements and useful in workplace ergonomics, your human factors. So MODAPS are developed by this guy, Haidt, in 1966. So MODAPS, what we use is we identify human motion, and we also code the human motion. So here you can see 1, 2, 3, 4, 5 parts of your hand, your fingers, and then your palm, and then your shin, and then your first part of your arm, and then the second, which is connected to your shoulder. So table 1 here is telling you the workers move a small box to a scale, weights it and sets it aside, and then returns the hand to the table edge. So here, that's how we use the MODAPS code. And this is a description of that. And here's the distance for each motion, okay? MODAPS are pretty easy to use because of its simplicity. So it has like, here in this example is there 21 elements. So there's variation, and you can see it's a little bit different from each company, but majority of them is like from 1 to 21 coding. And it can be used in almost every industry for work and study. So when you look at the code, you're going to see G0, okay, and then G1, then G3. This is like just touching or contact. So nothing here is you start to grab. So here everything from A all the way, okay, to Z. So when you look at G, you go back here, look at the table, and you're going to see that's get, okay, motion. Oh, when you look at P, then you're going to see right here, That's put motion. Okay. 2 is just telling you which part of your hand this motion is using. So we use MODAPS to evaluate production line test load, estimate labor book performance. We also use something called Argo mode measures the increase of test difficulties. Argo mode is nothing but we're studying the human factors and then use the coding for that. So it's just a system, and that system is going to give you analysis of the difficulty of the work. So here you can see it's in the basic apparel plant and sewing machines layout is right in there. So in automotive industry, like a Ford, is used automotive and transportation, they're like back to back. So there we use the MODAP as a method of establishing line test times. Again, Argo again, and then the corporate labor book performance. Okay. So we use MODAPs in automotive industry because the times are based on the observed movements. In the lab or assembly line, you will be doing MODAPs. Okay, so you gotta make sure how to recognize the motion of hand and don't go so fast, so you won't catch these movement, and you will go into micro motion study and come up with your MODAPS code. So PTSS is developed by Fred Myers, and it's just a time system that is really quick to learn and easy to apply. Okay. So what we do at PTSS is first we review the PTS table and then define the terms. And then we have the form to fill it up. And then we have 13-step procedure to follow. And then I'm going to give you the example problems, okay, so that you can be able to understand what PTSS is. So what it studies is it studies what causes the time of a job or jobs to vary, okay. So here's a PTSS table, and thus time for each motion is described right here on this form. And your table is a source of time standards for all motions that this form study. So when you look at the form and the table, you're going to see the left side is giving you your time standards in thousands of a minute. So that's 3 decimal, okay, for thousands. Here is your third, second, and then the first. We count in, we don't count out. So make sure you know the third is the last one. And then your right side is your motion pattern construction table. And then your bottom right side is your definition of terms. Okay, so we're going to start with definitions of terms. So the very first one is code R. R for reach. Okay, that's the first motion. So move the hand to a destination. Your example is reaching for a part or a tool. Okay, so in here is your code. You can see R, 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 and R right there. And if you see the code, you're gonna know that's reach. Okay, you're reaching for something, reaching for a tool. Here is your distance. This is your unit. So that's going 1 inch, okay? And this is going 15 inches, 3650, okay? Reaching 1 inch, reaching 15 inches, and so on and so on. So time in decimal unit. So here we have 1, 2, 3. So that's your thousand again. 4, 11, 21, and 27, okay? So when you see that, you're going to count with this unit, which is going to be 0.004. Okay, so we're going to count in, we don't count out. So this 4 is at your third decimal place. Okay, now that's your time. It's got to be really, really quick because it's going only 1 inch, okay, reaching 1 inch. Therefore, it has the shortest time, very minute time. And here is your explanation. So 1 divided by 2 plus 0.003, okay? Code small letter m. So when you look at the code a small letter m, you're going to see m at the end of our code means here, okay, the end of reach. So it's trying to tell you you're reaching 10 inches and then you're going to end that reach. So m preceding r means the beginning of reach. Here m, then you have your r, and then you have 20 inches going, okay? And this is your time standard respective for that motion. So example R10 m little m means reaching 10 units, ending in motion, and R20 means beginning in motion, reach 20 units. Okay, this units here in this example is your inches. So pretty easy, right? It's just about coding. So our assumption is motions are assumed to be made flat. Even if curved motions are made in some cases, we still take flat as our assumption. So now we have a move code, capital letter M, we call it big M. So that's move an object to a destination. So for example, moving a part from the bin to the fixture, okay? Move time is varied because the distance measured as in inches, beginning or ending in motion, you have it. And then weight or force is required because you're moving something. So move time for weight less than 5 pounds is definitely same as reach time, okay? So here is a table and here is your move symbol and respective motion. And here is your distance and also pounds for your weight. And your time, recorded time for each motion element right here. So now you know how to read it. Big M, 18. So you're moving 18 inches. You're moving 6 inches, ending that motion, okay? And here, this is again an explanation of little m, which is right here, ending and beginning. If you put your m at front, that is going to be beginning in that motion. So here in this table, you just see left hand, and then your time to fill for timestamp for each hand's motion, and here this side is your right hand. Sometimes you're going to see this type of table, so you can understand that we are studying your left hand and your right hand movement. Okay, so now you can read all of that. That's your R, that's your M, that's your R, that's your ending, your move, 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 your reach. Okay, and here are all your units. And that reach and move motions, they account for about 50% of all operator controlled work. Okay, we have two control work in a facility. One is operators and the other one is your machines or robots. Alright, so next series of code is your graphs, and that's code G. And we have G code all the way 1, 2, 3, 4. We also have regraphs, okay? That's your G4. Small parts or fingers, code G3. Medium parts will go G2. Large parts, you go with G1. And your contact is just code G, which is actually 0 at the end. So some people will use 0 at the end, some people will use without it, okay? I'm not going to I'm not going to go into details, so you can go ahead and read it. So what we're emphasizing is for you to be able to recognize each code, the letter, and then what they do, okay? Here again, your release code, your alignment is AP, A for alignment, and P is your position, okay? Releases are L for release. For alignment and position, we have 1, 2, and 3 different motion. So I want you to go over and read all of that. And the same way to code it and read it, all you have to recognize is a different motion. What is it doing? What this code is saying to you. For static force, we use SF. For your eye fixation code, we use EF. Eye trouble code is going to be ET. So we're getting into the motion and movement of your eye. Here, when you look at the cost reduction application, you can see this is just an exaggerated drawing, and you see the pin will be redesigned to add a jumper, that's your furrow, or a countersink. Okay, so it reduces from AP3, that's your alignment position, and that's your just 3 units going, alignment position, 2 units going, and saves a time value. So what we do is here, that's your point of engagement, and they are adding a little countersink right there. So we can be able to reduce AP3, that's your distance, 1 unit is off for that distance. So 3 to 2, we can reduce it. So that way we can save some more time, okay? Foot motion is your FM, and leg motion code is your LM. Turning, okay, is code T1 or T2. Bending, rising from the band is your B and AB. It's all about you picking up something. Okay, so here you can see is bending and then rising from bending. Same thing. Then stoop and rise from stoop. Again, getting into your leg motion. Code A and then AS. Sit and stand is your code ST. Okay. Again, what you're going to do is read through that and emphasize on learning the code letters and what they do. Okay. Walking code W underscore F and then F underscore P. So those are your working code. We measure by using feet or paces. Okay. For example, if I write like W10F, you're gonna walk 10 feet. W5P, you're gonna walk 5 paces. Okay. That's your feet and that is your paces. Special instance of walking, so code W underscore FO, W underscore PO. Okay. So if you see this code, you know that your walking motion around obstructed workstation and then sideways move your sidle. It takes about 25% more time than walking motion. So for example, receiving transported materials and obstruct the workstation. So in our miniature lab, the assembly line lab, you're receiving personal is transporting your parts to your workstation. And sometimes you're going to see the obstruction, okay, along that path. That's why it's slowing down. And then sometimes you drop your parts on to the floor. So that's what we're talking about, okay. So a special instance of working is applied until the end of material removal from that site. So you're picking up what you drop from the floor, okay. And at that time, we're going to use this type of coding instead of regular walking code. Time standard coding, example, code time standard for this picture right here. So that's our same thing. We use a gravity, okay, move the pin, and here is your loop. of your motion. So each motion places 2 pins in the ball in this example. So for 30 pins, you're going to divide by 2 and you're going to have total of 15 motions to do this job. Okay, so now we're going to divide it into left hand and the right hand, measure the time, and we'll be using your codes, okay, PTSS codes. R6, G2, M6, AP1. So we already know what they are. So that's your reach, okay, your get, your move, your align, and position, okay. So for 2 pins, one motion, it's going to take 0.029. Again, all our time is in 3 decimals, so that's your thousand. We're going to count backwards towards your decimal point. So that 29, if you see 29, this is how we read it, 0.029, okay? Times, we're running 15 times, so we get 0.435 here. Frequency, 15 times, okay? For 30 pins, so you get 0.435 minute in time. So your movements included in this motion are from here all the way to here, okay? And that is for left hand. From here all the way to here for your right hand. That's your break time, so plus 10% allowance. So we're taking a little bit of break. Your standard time, the same thing, pieces per hour. We have done it again and again. Hours per pieces, okay, 0.00800. So motion pattern construction table is telling us what we can do at the same time and what we cannot. So the intersection of left hand and right hand motion is shown in each cell of this table with 2 numbers, and we call these numbers motion pattern codes. So no number in the box means no motion, okay? And this table here, I have a typo right there. So this table is filled using code 1 all the way to 4. So code 1. First motion, full value. Second motion is your half value. So for example, you're going to grab 2 large parts, hands less than 10 inches apart. Okay, so here left hand, here right hand. G for grabs or get part, G for grabs or get part. So some of the code we say this gets or sometimes grabs, okay? So read 3 as 0.003 at third decimal place 4 times. Half of 3 is 1.5, which is, we're going to translate that to decimal unit and you get 0.0015. But rounded as 0.002, okay, our rounding system again, this 5. Therefore, taking us 2 for half value for second motion. So that's how we get the second motion, half value. The first motion, full value. Okay, 3. The other one is 0.0015, but we usually take it a rounded number, so pay attention to that. The first motion, full value. Second motion, full value for code 2. So for example, place 2 parts in the holes over 10 inches apart. Okay, left hand and then right hand. Alignment position 2 units. Alignment position 2 units. This time we're not dividing that by 2, okay, because we're taking the full value for your second motion. So either hand can go first. You can start with right hand or you can start with your left hand. Okay, so code 3, first motion, full value, okay, plus a 2-inch reach, or a move 2 inches plus second motion, full value. Second motion, full value. First motion, full value. So example, grabs 2 small parts over 10 inches apart. Aligning and positioning 3 inches. Gonna use 0.004 minute of move 2 inches, okay? Right after in this case. And when you look at the time, it's using 0.009, 0.004, 0.009 again, because that's the same full value, okay? And here is where showing the code with your reach code. So if you want to go with move code, you're going to put M right here, okay? The code for first motion, full value, plus we're going to go I trouble, so therefore ET. Doesn't say how many units, so just go 0. Plus second motion, full value, so the same 3 here and so 3 right there, okay? The second motion is different. The first one is your grabs, and the other second one is your align and position. So hands cannot do grabs. In align position AP3 at the same time, full value, okay? So therefore you need your eye trouble. So what we're doing here is we're doing a micro motion. So first you are doing a first motion, which is your grabs. Then you're going to change align position, all right? So at that time, you will definitely be needing to use your eye, okay? So therefore, we put the eye trouble between the two motions. You gotta go real slow motion in order for us to be able to recognize that eye trouble. So it's usually really fast, okay, happening. That's why I try to tell you to do 240 parts in our lab for 1 hour so that you can be able to recognize your own motion at each station instead of just talking to each other and do whatever. You have to concentrate in each motion to be able to see these movements of your hand, alright? But we still have 3 more times for lab, so make sure you recognize all these things while you're performing the motion study and time.